This plume in front of 3 Atlas leads, as if the object is dragging a halo of light behind an invisible prow. Instruments aboard orbiters around Mars recorded asymmetric halos that shimmer with patterns resembling magnetic contours rather than random puffs. The James Webb Space Telescope returned a chemistry that did not fit familiar catalogs. The ratio of carbon dioxide to water ice was 8:1, a composition more at home in worlds we do not yet understand. And then there was the timing. Between the 21st of November and the 5th of December 2025, 3 Atlas would pass behind the Sun. For nearly 2 weeks, it would be lost in the Sun's luminous cloak, a strategic blind spot where no optical sensor or radar can follow. Astronomers named that stretch the cosmic curtain. The phrase feels theatrical until you stand beneath that invisible theater and imagine what happens when a performer disappears from view at the most convenient moment. If a natural wanderer, this disappearance is mere geometry. If engineered, it is an interval of opportunity. Hidden from us, 3 Atlas could change in ways we would not detect until it re-emerges. It could release smaller objects. It could reorient itself. The voice in the back of the room, the one that listens for symmetries and messages, began to whisper possibilities that felt both reckless and necessary. You should know the story of 2 earlier vagabonds. In 2017, a cigar-shaped visitor known as Oumuamua slid through the solar system, tumbling and accelerating in directions that made little sense under known physics. It arrived like a folded note dropped into the ocean. In 2019, a more ordinary interstellar comet named Borisov arrived and behaved like the textbooks promised. Between those two, the universe seemed mercifully ordinary again. 3 Atlas arrives as a third voice, one that borrows from both predecessors and then writes a new dialect entirely. Consider the physics we depend on to read these motions. Comets shed material as they warm, sodium and water vapor and dust trailing in predictable ways. Radiation pressure shapes tails, solar wind scours, sublimation sculpts. But 3 Atlas refuses to obey the script. Its tail does not trail. Its mass is heavy, but its light behaves as if guided by an architecture. The brightness patterns shift with a deliberateness that unsettles the models. For all of its familiarity with dust and rock, the object acts like an instrument. Some scientists say that great mysteries first arrive as stubborn data. Then, if they survive scrutiny, they become hypotheses. Avi Loeb is one of those who prefers hypotheses that do not shy from radical possibilities. The notion that this object could be a probe designed for patience sounds extravagant until you remember how many times the improbable became ordinary in science. Radio was once a novelty. Quantum tunneling once read like incantation. Black holes were metaphysical curiosities before they demanded pages of sober mathematics. Suppose for a moment that 3 Atlas is artifice. Suppose it is a construct assembled with patience longer than epochs. To cross interstellar space requires either enormous time or propulsion far beyond ours. A probe could be small and fast, or it could be slow and patient. Small and fast risks detection in every passing century. Slow and patient is cunning. A craft cast into the void, sheltered by cold and vacuum, drifting until the right lens finds it. If a civilization wanted to study another, it might not land. It might not send messages in radio frequency. It might send an object that operates in silence, that aligns itself with orbital planes, so that when a species reaches a certain observational capacity, there it would be, a calibrated puzzle piece in a room the species could finally see. This thought is uncomfortable because it suggests a particular kind of intelligence, one that thinks in centuries and millennia, that values observation over diplomacy, that understands the patience required to wait for a species to grow into recognition. It posits motives alien to our accelerations. We live in epochs defined by quarterly reports and fast iteration. But cosmic patience operates on the cadence of star years. All of this unfolds against a backdrop of human breakthroughs that make the timing almost theatrical. In laboratories, our machines reached new thresholds. Quantum computing moved steadily from fragile experiment to plausible tool. Entanglement, that strange intimacy between particles across distance, became not only demonstrated, but harnessable in states that astonished even their inventors. W-state entanglement, the kind where a cluster of particles remains entangled in a way that is robust under loss, felt to many like the grammar of a deeper reality. If the universe is a language, then W-states are part of its syntax. At the same time, quantum processors began correcting their own errors fast enough to be useful. Error correction was the wall between promise and practicality, and breaking through it felt like teaching a newborn to stand with balance. Suddenly, problems with many interacting variables, from molecular simulations to market dynamics, folded into computable landscapes. In such a world, the boundary between observer and observed blurs. Measurement informs outcome. We were becoming not only interpreters of the cosmos, but participants in its unfolding. Humanity also flirted with the power that moves stars. Fusion, that promise of a miniature sun, reached new durations and stabilities in experimental reactors. To squeeze hydrogen into a sacrificial hearth and watch it yield more energy than it consumed is to hold a star's heartbeat in a laboratory coil. The utopian uses of that power are glorious to imagine. Desalination on continental scales, energy without carbon, the ability to lift entire regions out of scarcity. But the same capacity carries shadows. Energy concentrated at will invites both healing and harm. And then there were whispers from biology. Researchers began to turn back the cellular clock in ways previously impossible. A protein that acted as a switch for aging showed unexpected consequences when inhibited. Reprogramming somatic cells without erasing identity hinted at a future where organ systems could be rejuvenated without replacement. These were not mythological promises, but carefully measured experiments in mice, showing real reversal of age markers. The ethical and social questions proliferated faster than the data could keep pace. Imagine humanity at the moment when mastery of energy, information, and biology converge. We are moving into a space where our species could alter much that previously felt immutable. That context makes the arrival of 3 Atlas feel less like coincidence and more like an exam administered without a bell. The object does not shout. It arrives with the restraint of a proctor. When 3 Atlas approached the Sun, instruments tuned in with more intensity than usual. Telescopes traced its brilliance across spectra. Spectrometers disentangled the light into chemical fingerprints. The Webb telescope delivered the haunting CO2 dominance. Such a ratio suggests formation in environments alien to the trio of ice and rock we recognize. Could this composition indicate birth near a carbon-depleted star? Could it be residue of artificial processing that stripped away lighter, volatile signatures? The data do not make such leaps for us. It is our imagination that supplies the rest. Yet the rest is hard to ignore. And then the object slipped behind the Sun. For 14 days, the charts flattened, a gap in observation that felt oddly like waiting for a spine to finish a twist. During those days, sessions convened, protocols drafted. Some proposed using gravitational microlensing to guess whether the mass distribution had changed. Others imagined sending a trail of small craft to the sunward side to catch anything expelled. The limits of logistics and politics made many plans aspirational, not immediate. So we waited. What we did not do is stop thinking. That in itself is a strange human consolation. We are, collectively, a species that tells stories when we do not yet possess answers. The stories range from the prosaic to the sublime. Some narratives insisted on natural origins, on rare but possible coincidences folded into the vast randomness of space. Others proposed machinery, probes designed to test the waters of emergent civilizations. A few, speaking in measured speculation, suggested neither malice nor benevolence, but intentionality as a simple fact. Someone had thought to place a thing in a particular place. That hint of plan alters the way we imagine cosmic histories. When 3E Atlas re-emerged, the light was slightly different. Small, almost imperceptible shifts in brightness suggested a reconfiguration. The leading halo had broadened, and the plume now traced a subtle bifurcation that had not been visible before. Observers across the world leaned into the data like listeners into a piano. Patterns that had been whispers grew into coherent motifs. The trail carried microstructures that scattered light in symmetric ways. A fraction of the dust seemed arranged, not blown. The reactions were varied. Some teams cautioned against anthropomorphizing natural processes. They reminded us of complex plasma interactions that can produce ordered skin, like filaments from magnetic reconnection events. Others were less patient. They modeled scenarios where small autonomous probes, released from a larger shell, could use solar radiation pressure and magnetic field gradients to adjust trajectories. The math did not fail to support such maneuvers. A swarm of tiny, reflective objects can sail like salt crystals on a sunlit pond if the conditions are right. But that still leaves the central mystery unresolved. Who would assemble such a fleet? For what purpose? And why align it with planetary planes? Maybe the most unsettling possibility is not that some external intelligence is studying us, but that intelligence is not singular. What if the cosmos habitually sends such instruments like lesson plans in bottles? If civilizations come and go, perhaps they leave artifacts not for conquest but for conversation. A device that waits for a species to learn how to listen. The significance is not in contact alone, but in the patience of the messenger. To cast an object into interstellar space is to wager on time. It is to invest in futures you will not inhabit. The narrative steeped itself in metaphors that were almost inevitable. The object becomes a mirror. Its mathematics became poetics. Our new tools became instruments, not only of measurement, but of introspection. Quantum mechanics taught us that observation alters the observed. The philosophical shadow of that fact deepens when the observed might itself be intentional. Are we being measured? Or do we measure ourselves in the act of measuring? There is humility in the possibility that we are being noticed. There is terror too. What would it mean for human identity if an external intelligence decided to test us by sending a riddle across eons? Would we respond with curiosity or with weapons? Would we learn to reflect, to share, to extend a hand across the void? Or would fear become the more immediate reflex? The public reaction was a study in contrasts. Some became quieter, looking up more often at the night. Others used the story to accelerate funding for deep space probes and better solar observatories. Policy bodies argued about transparency and containment. The scientific method and the human appetite for narrative collided in editorial rooms and in quiet offices where data analysts worked into nights. The safest way forward felt like the slowest one, which suited the object perfectly. Patience had been a weapon in its favor. Perhaps patience would be the virtue that carried us through. People wrote poems. Children drew images of a glowing teardrop like a lantern with a tiny city inside. Philosophers debated whether intent requires mind. Priests found familiar metaphors. A language class coined new words for awe. Far from a monolith, human reaction fragmented into the familiar prismatic pattern of our species. A few months later, scientists proposed an ambitious mission to send a small sailcraft that could ride solar pressure to intercept 3 Atlas on a later path. The idea was not naive romance, but engineering grounded in what our technologies now permitted. Solar sails are slow but elegant, an interplay between light and thin reflective film. They were what we could build quickly and affordably to test the artifact hypothesis. If you are patient enough, light can move matter. The mission plan required something equally old-fashioned as patience: consensus, international collaboration, funding commitments, a shared set of goals that elevated understanding above possession. It was a test in another register, a social experiment as much as a scientific one. Could humanity cohere around curiosity when the prize was knowledge rather than ownership? All the while, 3 Atlas continued to pass. Its path took it toward the inner system, and then back outward in a slow arc that read like a sentence written across decades. Observations continued, and with them, the cycle of hypothesis, test, revision. Some anomalies resolved into natural explanations when models became more refined. Plasma dynamics can create leading structures under certain magnetic configurations. Volatile redistribution can yield surprising composition readings when mixed with a background of processed ices, yet other details stubbornly resisted tidy resolution. Perhaps this is the essential lesson. The universe does not have to be either benign or hostile. It can be enigmatic. It can offer puzzles that teach us how to learn. 3 Atlas magnified a truth that had been whispering for some time. Our instruments are not only ways of taking in the world, they are ways of becoming a species worthy of being observed. Night after night, as the world tracked the visitor, a kind of quiet acculturation happened. We asked whether every discovery should incite exploitation, or whether some things deserved reverence. We recognized that power without wisdom corrodes. Our newfound capacities in energy, computation, and life extension suddenly tasked us with questions as much ethical as technical. Could we grow wisdom at the same rate we grew capability? That is the question the object posed, not with words, but with presence. In the end, 3 Atlas may remain ambiguous. It may be an extraordinary natural object that stretched our models and expanded our vocabulary of the possible. It may be a relic of an intelligence older than our myths. It may be a mirror that reflected our readiness or unreadiness to be part of a larger conversation. Whatever the true provenance, it altered the way we looked at each other and at the cosmos. When the visitor finally receded into the starlit plain, leaving behind trails of dust that continued to whisper in the thin solar wind, humanity had already changed. The telescopes had catalogued data that would fuel research for generations. The mission concepts had matured into real commitments. The public had discovered a common sky that felt more intimate than ever before. And in a quieter corner of the night, some of us still look up, not to own the answer, but to sit with the question. We listen for patterns in the dark and try to learn the grammar of patient things. We are learning to keep silence when silence is needed, to accelerate when kindness is necessary, and to wait when patience might reveal a larger story. So tonight, before you drift off, imagine a teardrop of ancient light cutting a slow arc around our sun. Imagine the delicate mathematics that aligned it with planetary planes like a choreographer marking a stage. Imagine a plume that chooses to lead and not follow. Imagine the small acts of courage required to answer, across a species, that silent question. In the quiet after candles gutter, we are, perhaps for the first time, practiced watchers. We are practicing the humility to be observed and the courage to respond without haste. Whether 3E Atlas is artifact or rock does not change the deeper truth. The universe has become a mirror, large enough for us to see beyond ourselves. Sleep now, under a sky that keeps sending invitations and mysteries. Tomorrow we will read the data again and argue respectfully. Tonight, let the stars hold their counsel. Let the thought of an ancient visitor fold you into wonder. Good night from Bedtime Universe. Welcome to Bedtime Universe. Here, every night is a journey across the endless sky. Close your eyes and let the stars whisper their stories. Let's go to the story. The alert came through at 3:47 a.m. Pacific Time, a rhythmic chime that pulled Dr. Ilara Vance from the shallow sleep she'd been managing in the observation lounge at the Jet Propulsion Laboratory. Her tablet's screen glowed with the automated notification from the Atlas survey system in Hawaii, a new fast mover with an orbital eccentricity that made her breath catch even before her coffee-deprived brain fully processed the numbers. Eccentricity 1.93. Hyperbolic, decisively hyperbolic. She was moving before conscious thought caught up, her fingers already composing the emergency convocation message to her rapid response team, while her feet carried her down the familiar corridors toward the small body dynamics lab, the fluorescent lights flickering to life in sequence, as motion sensors detected her passage through the pre-dawn stillness. By the time she reached the lab, 3 other astronomers had already materialized, drawn by the same siren call of impossible orbital parameters, their faces illuminated by the blue-white glow of multiple monitors, displaying preliminary trajectory solutions that all pointed to the same extraordinary conclusion. This object, provisionally designated 3I divided by Atlas, had not originated from anywhere within our solar system's gravitational embrace, but had instead fallen toward our Sun from the vast interstellar gulf. Only the 3rd such visitor humanity had definitively identified, and the first since 2I divided by Borisov had departed in 2020. Ilara's colleague Marcus Chen was already running confirmation protocols, his hands dancing across keyboards as he queried every available Sky Survey database for Precovery images, any photographic plate or digital archive that might have captured this traveler before Atlas had flagged it, anything that would extend the orbital arc and tighten the uncertainty ellipse that currently smeared across millions of kilometers of possible positions. The preliminary solution suggested a perihelion distance of just 0.032 astronomical units, less than 1/30th the distance from Earth to the Sun, a trajectory that would bring this interstellar visitor screaming through the solar corona at velocities exceeding 290 kilometers per second relative to the Sun, subjecting whatever material composed its surface to thermal and radiation environments that would vaporize ordinary rock and sublime any volatile ices in spectacular fashion. They had perhaps 6 weeks, maybe 7 if the photometric models held, before 3I divided by Atlas would be lost to them forever, first to the blinding glare of solar conjunction as it passed behind the Sun from Earth's perspective, then to the infinite dark as its hyperbolic orbit carried it back out past the heliopause and into the interstellar medium from which it had emerged. 6 weeks to characterize something that had potentially traveled for millions of years through the frozen desert between stars, carrying within its structure clues to the chemistry and physics of planetary systems so distant their light had not yet reached human eyes, or perhaps carrying something stranger still, though Ilara suppressed that thought with practiced scientific discipline, even as it flickered at the edges of her consciousness. The confirmation came within 18 hours, as observatories across the globe turned their attention to the coordinates Atlas had provided. Each new position measurement, refining the orbital solution until the hyperbolic nature of the trajectory became not just probable, but certain, the systematic deviation from any closed orbit, eliminating the possibility of measurement error or computational artifact. The International Astronomical Union's Minor Planet Center issued the official designation, and suddenly Ilara's team was at the center of a global astronomical effort that reminded her of the frantic weeks following the discovery of Oumuamua. Except this time they had advance warning of the perihelion approach and sophisticated models of interstellar object behavior, informed by 2 previous encounters. Though, as she would soon discover, those models would prove woefully inadequate for understanding 3I divided by Atlas. The first spectroscopic observations came from the Very Large Telescope in Chile, where the European Southern Observatory had granted emergency directors discretionary time, bumping scheduled observations to capture the weak reflected sunlight from an object still more than 2 astronomical units distant. Ilara stood in the JPL analysis theater with a dozen other scientists, the curved wall displaying the reduced spectrum in high resolution, and felt the familiar thrill of discovery transform into something more complex, a mixture of excitement and unease that she couldn't immediately articulate. The spectrum showed emission lines consistent with outgassing, confirming that 3I divided by Atlas was active like a comet, despite its interstellar origin. But the relative intensities were all wrong. The hydroxyl radical emission, that ubiquitous signature of water sublimation that dominated every cometary spectrum she'd ever analyzed, was strangely muted, barely rising above the noise floor. Instead, the spectrum blazed with carbon monoxide emission, far more CO than should exist relative to water if this object had formed in a protoplanetary disk, even remotely similar to our own. Marcus noted the anomaly first, his voice careful and measured as he highlighted the line ratios on the display, suggesting contamination or instrumental artifact, before allowing himself to consider that the observation might be genuine. But as subsequent observations from Keck and Gemini confirmed the same bizarre composition, the team had to confront the possibility that 3I divided by Atlas represented a genuinely alien chemistry, perhaps an object formed in a stellar system with radically different volatile abundance patterns, or something that had experienced thermal processing during its interstellar journey that preferentially depleted its water content while preserving more refractory species like CO. The photometric campaign revealed additional strangeness that defied easy categorization. Unlike the relatively stable light curve of 2I divided by Borisov, or the dramatic tumbling rotation of Oumuamua, 3I divided by Atlas exhibited irregular brightness variations that seemed almost chaotic, fluctuations of up to 0.7 magnitudes, over timescales ranging from hours to days, with no clear periodicity that would indicate simple rotational modulation of an irregularly shaped body. Ilara's graduate student, Yuki Tanaka, spent sleepless nights trying to model the light curve using every combination of shape, albedo variation, and viewing geometry her software could generate, but nothing produced a satisfactory fit to the observations. The object seemed to be changing its cross-sectional area or reflectivity in ways that suggested either an extremely complex shape undergoing precession, active surface processes that altered its reflective properties on short timescales, or some form of mass loss that was more dramatic and variable than typical cometary activity. The latter hypothesis gained support when high-resolution imaging from Hubble, scheduled during a brief gap in the telescope's crowded observation calendar, revealed an asymmetric coma structure that didn't conform to the expected fountain model of dust and gas, expanding radially from a sublimating nucleus. The images showed what appeared to be discrete jets or plumes emanating from specific locations on the rotating body, but their activity patterns didn't correlate with solar heating in any straightforward way. Some jets seemed to activate and deactivate on timescales too short to be explained by thermal inertia, while others persisted through the object's rotation into the night side, where solar radiation should have been insufficient to drive sublimation. Ilara found herself presenting these anomalies to an emergency convocation of the Planetary Science Division, her carefully worded analysis, emphasizing the scientific uncertainties while trying to avoid the sensationalist speculation that was already proliferating in various online astronomy forums and tabloid publications. She knew that Oumuamua had spawned endless debates about its potentially artificial nature, arguments that had consumed enormous amounts of professional time and energy while generating more heat than light, and she was determined to keep the investigation of 3I divided by Atlas grounded in rigorous observation and conservative interpretation, even as the object's behavior strained the boundaries of conventional cometary models. But privately, in the quiet hours of early morning when she reviewed the data streams alone in her office, Ilara couldn't entirely suppress the recognition that they were observing something genuinely unprecedented, an object whose properties existed in parameter space that no known natural process could easily populate, at least not according to current understanding of small body physics and interstellar medium chemistry. The non-gravitational acceleration complicated everything further. As the orbital solution refined with each passing day of astrometric observations, the trajectory calculations began showing systematic deviations from a purely gravitational path, the telltale signature of rocket-like forces imparted by asymmetric outgassing as volatile material, sublimated from the sunward-facing surface and created thrust through momentum exchange. Such effects were well documented in conventional comets and had been observed in Oumuamua as well, providing a natural explanation for that object's deviation from a Keplerian orbit and removing the need for more exotic hypotheses about solar radiation pressure acting on an artificial light sail. But the magnitude and direction of 3I divided by Atlas's non-gravitational acceleration didn't correlate with the observed outgassing activity in any sensible way. The acceleration vector seemed to lag the subsolar point by an angle that changed over the course of the object's rotation, suggesting either an extremely complex surface distribution of volatile sources or some form of thermal processing that created long-lived hotspots capable of driving sublimation hours after direct solar illumination had ceased. Marcus developed elaborate models incorporating subsurface heat transport, porosity-dependent thermal diffusion, and heterogeneous composition maps, but even his most sophisticated simulations couldn't reproduce the observed acceleration vector without invoking parameter values that existed well outside the range measured for any known cometary nucleus. The team's internal discussions grew increasingly animated as perihelion approached, with Ilara finding herself mediating between those who insisted on explaining every anomaly through increasingly contrived natural mechanisms and those who cautiously suggested that they might need to consider hypotheses outside the standard model of small body behavior. The phrase, "we should keep an open mind," became a battlefield, with each side accusing the other of either close-minded conservatism or reckless speculation, depending on which direction the intellectual openness was supposed to extend. Ilara tried to steer a middle course, insisting that extraordinary claims required extraordinary evidence, but acknowledging that the evidence they were accumulating was itself becoming rather extraordinary, a collection of anomalies that individually might be dismissed as measurement uncertainty or modeling inadequacy, but collectively painted a picture that didn't quite fit any existing template. The political pressure intensified as media attention focused on the mission, with the JPL director fielding calls from congressional staffers wanting to know whether taxpayer dollars were being used to investigate alien spacecraft, a characterization that made Ilara's teeth clench every time she heard it because it fundamentally misrepresented both the team's scientific approach and the nature of the anomalies they were documenting. She drafted carefully worded press releases, emphasizing that all observations remained consistent with a natural object of exotic composition, and that the scientific process required patience and systematic investigation rather than premature conclusions. But she could sense the institutional nervousness about another Oumuamua-style controversy that might damage JPL's reputation for sober scientific analysis. The countdown to perihelion became the organizing principle of her existence, each day bringing the object closer to that blazing closest approach, while simultaneously making observations more difficult, as 3I divided by Atlas's elongation from the Sun decreased and the sky background brightened. The team worked in shifts to maximize telescope time allocation, coordinating observations from facilities around the world to maintain nearly continuous coverage as the object accelerated inward, its heliocentric velocity climbing toward values that made orbital mechanics feel visceral rather than abstract. At 2 astronomical units, they measured rotation periods and refined the spectroscopic inventory of outgassing species. At 1 AU, they detected silicate emission features, indicating dust production, and obtained thermal infrared observations that constrained the nucleus temperature and size. At half an AU, the solar conjunction geometry forced them to rely on spacecraft data, including an audacious proposal to correlate 3I divided by Atlas's trajectory with pointing data from the Parker Solar Probe, which was then engaged in its own death-defying plunges through the solar corona, as part of its mission to study the Sun's outer atmosphere and the acceleration mechanisms of the solar wind. The Parker correlation proposal came from Yuki, who had spent weeks analyzing spacecraft telemetry and realized that one of Parker's perihelion passes would bring it within the same general region of space that 3I divided by Atlas would transit approximately 8 hours earlier, separated by millions of kilometers, but close enough in the vastness of the inner solar system that the probe's instruments might detect enhanced dust or volatile species. If 3I divided by Atlas shed significant material during its closest approach, the idea was technically brilliant and operationally insane, requiring emergency reprogramming of Parker's data collection protocols during a phase of the mission when the spacecraft was already operating at the edge of its thermal tolerances, its heat shield facing the full fury of the solar corona, while its instruments peeked around the shield's edges to sample plasma conditions that no other human-made object had ever survived. The proposal triggered heated debates within NASA's heliophysics division, with mission planners arguing that any alteration to Parker's observation sequence risked compromising primary science objectives and potentially endangering the spacecraft if thermal constraints were violated. But the sheer scientific opportunity represented by 3I divided by Atlas's passage through Parker's observation volume eventually won out, helped by Ilara's impassioned presentation to the mission directorate, emphasizing that this was likely a once-in-a-generation chance to observe an interstellar object under the most extreme conditions imaginable, conditions that would either vaporize it entirely or drive outgassing at rates that would reveal definitive information about its internal composition and structure. The final week before perihelion felt like existing in a permanent state of controlled chaos, with Ilara sleeping in her office when she slept at all, sustained by caffeine and the electric anticipation of imminent discovery. The last direct Earth-based observations came from the Solar Dynamics Observatory, which managed to capture 3I divided by Atlas as a dark speck, transiting the solar disk during a brief window when the geometry permitted, the object's silhouette, providing one last astrometric data point before it plunged into the observational blind zone created by solar glare. The transit images showed an elongated profile, consistent with either a highly irregular shape or possibly a bifurcated structure that suggested the object might be a contact binary two lobes of material held together by tenuous gravitational attraction, though the resolution was insufficient for definitive morphological conclusions. Then came the waiting. 37 hours of near-complete observational blackout, while 3I divided by Atlas made its closest approach to the Sun at a distance of 4.8 million kilometers, plunging through regions where the ambient temperature exceeded 2000 Kelvin, and the solar wind density was more than 1,000 times its value at Earth's orbit, an environment so hostile that no spacecraft had ever operated successfully within it, except Parker and the earlier Helios probes with their specialized thermal protection systems. Ilara tried to occupy herself with data analysis and paper writing, but found her attention constantly drifting back to the countdown timer she'd set up on her secondary monitor, watching the minutes tick down to Parker's scheduled observation window, when the spacecraft would execute its own perihelion passage and begin searching for any trace of 3I divided by Atlas's passage through that inferno. The Parker data arrived in compressed bursts as the spacecraft emerged from behind the Sun and re-established contact with the Deep Space Network. The telemetry first, confirming that the spacecraft had survived its close approach, with all systems nominal, then beginning to downlink the science observations that would take hours to fully transfer given the spacecraft's distance and the limited bandwidth of its high-gain antenna. Ilara's team gathered in the mission support area, watching the progress bars slowly fill as gigabytes of detector data made their way across 150 million kilometers of space at the speed of light. Each completed file immediately fed into the automated processing pipeline that would calibrate and reduce the raw observations into usable scientific measurements. The first indication that something remarkable had occurred came from the Solar Probe Cup instrument, which measured the flux and composition of solar wind plasma flowing past the spacecraft during its perihelion passage. The nominal solar wind parameters showed the expected variations as Parker traversed different magnetic structures in the corona, but embedded within that data stream was a brief, anomalous interval lasting approximately 90 seconds, where the particle flux exhibited unusual enhancement in both density and temperature, accompanied by a compositional spike in carbon monoxide and other volatile species that had no business existing in the solar corona in those abundances. The timing and location of the enhancement matched almost perfectly with where 3I divided by Atlas should have been 8 hours earlier, assuming the object's predicted trajectory remained accurate, suggesting that Parker had flown through the residual wake of material shed by the interstellar visitor during its closest approach, a tenuous stream of gas and dust that had been stretched along the orbit by differential solar wind drag and was now dispersing into the corona. Marcus immediately began modeling the dispersion dynamics, trying to back-calculate the mass loss rate required to produce the observed enhancement, and arrived at numbers that seemed absurdly high, suggesting that 3I divided by Atlas had shed something like 5 to 10% of its total mass during that single perihelion passage, a fragmentation event more dramatic than any previously observed, cometary outburst and reminiscent of the catastrophic disruption events seen occasionally when sun-grazing comets failed to survive their close encounters with solar heating. But the wide-field imager for solar probe data told a different and more perplexing story. The high-resolution imagery captured during the observation window showed no sign of catastrophic fragmentation or diffuse debris clouds that would indicate complete disruption of the nucleus. Instead, the images revealed what appeared to be an intact object, still maintaining structural coherence, despite having just survived temperatures and radiation fluxes that should have vaporized most known materials. The photometric analysis showed that 3I divided by Atlas was significantly fainter than it had been during the final Earth-based observations, consistent with substantial mass loss, but the morphology remained relatively compact rather than diffuse, suggesting that whatever had been shed during perihelion passage had been lost in discrete events rather than through continuous erosive ablation. And there, embedded in the highest resolution frames, was the feature that would ultimately define the entire mission and generate debates that would continue for years afterward. A geometric regularity to the object's brightness distribution that didn't match any natural surface texture pattern, a series of what appeared to be planar facets reflecting sunlight at angles that suggested either crystalline structure or something more deliberately organized. The imagery right at the threshold of resolution where definitive interpretation became impossible, but suggestive patterns tantalized the imagination. Elara stared at the enhanced images for hours, rotating them through different contrast stretches and filtering algorithms, trying to determine whether the apparent geometry was real or merely an artifact of image processing and human pattern recognition bias. That cognitive tendency to see order in randomness that had plagued astronomical interpretation since ancient astronomers saw animal shapes in random stellar configurations. She convened 3 separate independent analysis sessions, where different team members examined the data without prior exposure to each other's interpretations, trying to establish whether the geometric features were consistently detectable across different analysis methodologies or dissolved into noise when examined with sufficient rigor. The results were maddeningly ambiguous, with some analysis chains clearly showing the planar features, while others reduced them to statistical insignificance, depending on the specific pre-processing steps and enhancement algorithms applied. Marcus argued passionately that they were seeing crystalline structure, that 3I divided by Atlas might be composed partially of exotic high-temperature materials like graphite or silicon carbide that could form macroscopic crystallites under the right conditions, creating large-scale facets that would reflect light coherently and produce the geometric patterns in the imagery. It was an elegant hypothesis that explained the object's survival of perihelion heating while accounting for the unusual geometric features. And Elara wanted to believe it because it preserved the natural origin interpretation while acknowledging the genuinely anomalous observations. But Yuki quietly pointed out that the facet orientations, if they were real, didn't correspond to any obvious crystallographic symmetry that would emerge from natural crystal growth processes, and that the distribution of bright facets seemed to show preferential orientation toward the sun in a way that suggested functionality rather than accident. Though she emphasized that this observation was highly preliminary and might not survive more rigorous geometric analysis. The team's final report, submitted to Science and released simultaneously to the astronomical community and the press, walked an intellectual tightrope that Elara knew would satisfy no one completely, while hopefully avoiding the worst excesses of either premature certainty or sensationalist speculation. They documented the extraordinary properties of 3I divided by Atlas comprehensively. The anomalous volatile composition dominated by carbon monoxide rather than water, the irregular light curve variations that defied conventional rotational modeling, the non-gravitational acceleration vector that didn't correlate simply with observed outgassing, the survival of extreme perihelion conditions that should have destroyed a conventional cometary nucleus, and the geometric features tentatively detected in the Parker Solar Probe imagery that might indicate large-scale crystalline structure, or possibly something more organized, with the critical caveat that the resolution limits made definitive interpretation impossible. Their conclusion emphasized that while all observations could potentially be explained by a natural object with exotic but not impossible properties, the collection of anomalies placed 3I divided by Atlas in a genuinely unique position within the taxonomy of small bodies, representing either an interstellar object formed under radically different conditions than those that prevailed in our own solar system's protoplanetary disk, or possibly an example of a formation mechanism or evolutionary pathway that remained poorly understood within current planetary science paradigms. The phrase that would be quoted and debated endlessly appeared near the end of the discussion section, the result of 3 hours of team wordsmithing to capture their genuinely uncertain epistemic state. We cannot exclude the possibility that 3I divided by Atlas represents an engineered object, or at least an object whose properties reflect processes not currently encompassed by our understanding of natural small body formation and process. Evolution, though we emphasize that this conclusion emerges not from any single definitive observation, but from the cumulative weight of multiple anomalies that collectively strain conventional explanatory frameworks. The media response was predictable and frustrating in equal measure, with headlines ranging from "Scientists confirm alien probe visited solar system" to "JPL team debunks latest interstellar UFO hysteria." Neither characterization, capturing the carefully calibrated uncertainty team had tried to convey. Elara found herself giving dozens of interviews, repeatedly explaining the difference between acknowledging the limitations of current understanding and making positive claims about alien technology, emphasizing that science advanced through exactly this kind of encounter with anomalous data that didn't fit existing models, that the point wasn't whether 3I divided by Atlas was natural or artificial, but rather what its properties could teach us about the diversity of possible outcomes in planetary system formation and evolution. Some of her colleagues criticized the team for even mentioning the possibility of engineered origins, arguing that such speculation gave legitimacy to fringe theories and undermined public confidence in scientific rigor. Others criticized them for not going far enough, for hedging their conclusions with so many caveats that the genuinely extraordinary nature of the observations got buried in scientific caution. Elara defended their approach as honest reporting of genuine uncertainty, noting that the data simply didn't support strong conclusions in either direction, and that pretending otherwise would be more damaging to scientific credibility than acknowledging the limits of current knowledge. In the months following perihelion, as 3I divided by Atlas receded back into the outer solar system and eventually beyond the reach of even the most sensitive telescopes, Elara and her team continued analyzing the archived observations, publishing detailed follow-up papers on specific aspects of the object's behavior and refining their models with the benefit of more time for careful analysis. The geometric features in the Parker imagery remained controversial, with some analysts claiming to detect additional evidence of structure in reprocessed data, while others argued that the features dissolved into noise when proper statistical corrections were applied. Several theoretical papers appeared proposing various natural mechanisms for 3I divided by Atlas's anomalous properties, invoking exotic ice compositions, complex thermal differentiation processes, or formation in unusual stellar environments, each model explaining some subset of the observations while struggling with others. The debate continued in scientific conferences and journal pages, a productive uncertainty that drove new theoretical work on interstellar object properties and motivated proposals for future missions capable of closer encounters or even sample return from the next interstellar visitor that graced the prude inner solar system with its presence. Elara found herself strangely content with the ambiguity, recognizing that the question of 3I divided by Atlas's nature might remain genuinely unresolved for decades or longer until either additional interstellar objects provided comparative context or technological advances permitted observations currently beyond reach. She thought about the object sometimes during quiet moments, imagining it rushing outward through the heliopause and back into the interstellar medium, carrying its secrets with it into the vast dark between stars, perhaps to be studied again by other civilizations orbiting other suns in the distant future, or perhaps to travel forever unobserved through the cosmic void, a mystery that would remain forever beyond human reach. The experience had taught her something about the nature of scientific understanding, that there existed a space between knowledge and ignorance, where honest uncertainty was not just acceptable but essential, where the proper response to genuinely anomalous data was neither premature certainty nor reflexive dismissal, but rather sustained engagement with the unknown, a willingness to sit with discomfort and allow mysteries to remain mysterious until time and better observations revealed clearer answers. She kept one of the enhanced Parker images on her office wall, that tantalizing glimpse of geometric patterns that might be crystalline facets or might be artifacts or might be something stranger still, a reminder that the universe remained fundamentally mysterious despite centuries of scientific progress, that there existed phenomena at the edges of human experience that defied easy categorization, and that the proper response to mystery was not to prematurely resolve it through convenient assumptions, but rather to approach it with humility, rigor, and wonder, acknowledging that some questions might not have simple answers, and that the pursuit of understanding was often more valuable than any particular conclusion. Years later, when other interstellar objects were detected and studied, providing comparative context for 3I Divided by Atlas's anomalous properties, the scientific consensus would gradually shift toward recognizing it as an extreme example of natural diversity rather than evidence of artificial origin, though a minority of researchers continued to argue that certain features remained inadequately explained by conventional models. But on that evening, when the final data was compiled and the last papers submitted, Ilara stood on the JPL campus under the California stars, looking up at the sky that held mysteries beyond counting, and felt profoundly grateful to have been present for this encounter with the genuinely unknown, this moment when humanity had briefly touched something that had traveled between the stars and found itself unable to fully comprehend what it had encountered, a reminder of how much remained to be discovered and how far we still had to go before claiming any complete understanding of the cosmic environment we inhabited. Hello everyone. Welcome to Bedtime Universe. Tonight, as the house quiets and the moon keeps its patient watch, we follow a traveler that is older than our memories, a small, cold wanderer that has crossed seas of empty space and the slow churn of stars, to arrive, for a while, within our sun's light. We call it 3I Divided by Atlas. Others have seen its faint glow through the long lenses of observatories and the steady gaze of telescopes. Scientists have traced its path across the dark, and instruments have listened for the telltale signatures of water and ice. Tonight I will tell you what we know, what it might mean, and why the arrival of 3I Divided by Atlas is as much a story of curiosity as it is of cosmic chance. Imagine a speck on the black. Imagine something smaller than a city, perhaps a relic of a distant planetary nursery, picking its way between the gravity wells of unnamed suns. For most of its life it has been alone, a frozen, silent artifact drifting through the interstellar medium. But across unimaginable distances, the push and pull of planets, the whisper of passing stars, and the slow decay of orbital motion conspire differently for every tiny body. Once in a great while, one finds itself bent into a new trajectory that brings it to visit another star. We did not always notice these visitors. Only with patient sky surveys did we begin to recognize them for what they are: travelers from elsewhere. 3I Divided by Atlas first came to human attention because of an automated sentinel, the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Its telescopes sweep the night, alert for moving specks that might one day be dangerous to us. On a clear night, early in July of 2025, a faint object moved where background stars did not. At first, it was only another dot in a long list, but follow-up observations peeled back the numbers. Its path was not elliptical like a comet tied to our sun, but hyperbolic, a path that would carry it through and away, not bound to our system. It was an interstellar interloper, the third reliably identified of its kind to meet our instruments. Those first headlines were quick to call it exotic, mysterious, perhaps even magical. Yet, the work that matters is quieter. Careful pointing of telescopes, the steady drip of spectral measurements, and patient calculations that transform raw data into a story. Astronomers trained their optics on 3I divided by Atlas from instruments across the globe, and in space, ground-based giants that collect faint photons, space telescopes that peer past Earth's air, and ultraviolet-sensitive instruments that read the fingerprints of molecules. The result was a portrait of a visitor that wears a ghostly halo, a coma, and a gentle tail, the signature of a comet. You may ask, comets are made of ice and dust. How do we know this object came from a place beyond our sun? The answer lies in its motion. Its orbit is hyperbolic, its velocity too high to be captured by the sun's gravity. This tells us it carried with it a history not formed here, and yet its behavior challenges the tidy categories we have. While some earlier interstellar visitors were bone-dry rocks or carbon-rich fragments, 3I divided by Atlas showed signs of water, or more precisely, its chemical byproducts, long before it reached the inner part of our system. Detecting water at great distances is not trivial. Water itself is not easily visible from afar, but when water molecules are excited by ultraviolet sunlight, they can break apart into fragments that emit light at specific wavelengths. One of these fragments is the hydroxyl radical OH, and its signature in ultraviolet light betrays the presence of water sublimating into gas. Instruments tuned to the ultraviolet detected OH emission around 3I divided. TLASLS, when it was still several astronomical units from the Sun, much farther than the distance where the familiar comets of our skies typically begin to boil off. They're ices. This unexpected activity raises a number of fascinating possibilities. First, the composition of 3I divided by Atlas might be richer in volatile ices than many comets observed in our own solar system. Perhaps it retained fragile, shallow reservoirs of water ice, protected by a porous matrix of dust that began to release when warmed slightly by the sun's reach. Or perhaps structural fragility allowed interior ices to become exposed by cracks and fractures as the body experienced mechanical stress during its interstellar journey. Another possibility is that the object contains more reactive or uncommon ices, like molecular oxygen, or trapped gases that respond to sunlight at greater distances, releasing water indirectly. Each of these scenarios tells us something different about how small bodies form and evolve around other stars. As discoveries go, this one is intoxicating because it underlines a truth. Objects that come from beyond our system are not all the same. Oumuamua, the first discovered interstellar object, behaved oddly pancake, or cigar-shaped, tumbling, showing a slight acceleration without the usual sign of outgassing. Borisov, the second, resembled a classic comet, trailing gas and dust with clear spectral signals of volatile molecules. Now 3I divided by Atlas adds a third voice to the chorus, a body that seems to carry abundant water or water-bearing materials even at a far remove from the Sunday. Like the samples of a foreign land, each one hints at the variety of planetary formation processes happening across the galaxy. It is tempting in the human way to spin grander tales. Across social media and opinion columns, speculation soared. Some suggested that an anomalous signal or unexpected brightness could indicate an artificial structure. These ideas attract attention and headlines precisely because they offer drama and the promise of rewriting our place in the cosmos. But rigorous science asks for more than drama. It asks for repeatable evidence, for measurement, for cautious inference. rooted in an understanding of noise, instrument response, and the physics we know. At present, the most parsimonious reading of the data is that 3I divided by Atlas is natural. Its coma and tail are consistent with sublimating volatiles and dust. Its spectral fingerprints align with molecules we understand. That does not close the door on wonder. On the contrary, a comet rich in water from a distant system opens new chapters in our understanding of how life-nurturing materials are distributed across the galaxy. Water ice can be a vehicle for organic chemistry, for the prebiotic reactions that lay the groundwork for life as we know it. If other systems produce and scatter icy bodies like this, they participate in a shared exchange of solid matter across the interstellar medium. Let us dwell for a moment on the human reaction to such events. When astronomers announced these detections, the public consumed the story in two overlapping ways: as a headline of novelty and as an invitation to contemplate. For some, the news was a scientific curiosity, another checkmark in the catalogue of rare objects. For others, it rekindled the older myths of messages in the night, comets as omens, as heralds, as carriers of meaning. Our culture carries a deep appetite for narratives that place us at the center of cosmic action. The steady work of observatories, however, asks us to temper our narratives with measurements. The real enchantment is that the universe is subtle and diverse, and that our tools have become good enough to see its nuance. Observationally, what does it take to see 3I divided by Atlas? For the casual stargazer, the object will remain faint beyond naked eye visibility. Its magnitude, the measure astronomers use for brightness, keeps it in the realm of small telescopes and dedicated imaging. But that scarcity of visible brilliance does not diminish the value of watching. Amateur observatories, armed with modest telescopes and CCD cameras, contribute to the dataset. Long exposure photographs, careful timing, and community coordination produce positional measurements that refine orbit models and feed larger analyses. In a way, the comet invites participation. The more eyes and instruments pointed at it, the richer the story we can tell. Behind the data are the laboratories and the instruments, ultraviolet spectrometers, large aperture reflectors, and space-based telescopes. Each records a different piece of the comet's nature. Ultraviolet readings reveal fragments from molecular breakup. Infrared observations trace thermal signatures and dust, and optical spectra find the fingerprints of molecules by their absorption and emission lines. Combined, they form a mosaic. The OH emission stands out because it is a clear, interpretable sign of water being liberated, and its early detection forced theorists to confront ideas about the thermal and structural behavior of small bodies in interstellar space. Why would a comet hold on to water for so long and then only start to release it far from the sun? In the cold dark between stars, ices bind into porous structures. Collisions, cosmic rays, and simply the passage of time change their microstructure. If an object formed far from its host star, in the freeze of an outer disk, the ices may be abundant and volatile rich. But if that object also spent eons drifting in interstellar space, subtle heating during stellar encounters or tidal interactions could have altered its surface. Perhaps the outermost grain layer was friable and easily lifted by even gentle thermal stress, releasing subsurface volatiles at greater heliocentric distances than we usually see. Another thought: interstellar space is not empty. It contains clouds of dust and gas, magnetic fields, and the remnants of previous stellar winds. A body passing through varying environments might accrete or lose materials in unpredictable ways. We must also consider that our models of sublimation are calibrated to solar system comets, whose histories of formation, collisions, and thermal evolution are anchored to the Sunday. An alien comet story could include phases and processes unfamiliar to our datasets. These are not just academic details. They are the threads of a larger tapestry describing how planetary systems seed the galaxy with raw materials. Beyond the science, there is a quieter human benefit to such discoveries: humility. We are reminded that the universe hosts a variety of experiments in planet formation. Each interstellar object is a single sample from a near-infinite experiment performed by nature. We cannot, from one visitor, claim to know all the recipes for planetary systems, but we can begin to assemble a statistical picture. Some systems produce dry, scattering rocks. Some send icy messengers. Some may eject fragments rich in organics. Over time, the collection of these observations will allow us to infer the diversity of planetary architectures across the galaxy. As 3I divided by Atlas continues its passage, instruments will track its brightness, spectrum, and morphology. Scientists will watch for changes. Does the coma swell as it warms? Does the tail shift direction as dust grains respond to solar radiation pressure? Will new gas species reveal themselves as different ices begin to sublimate at increasing temperatures? Each change is a tiny revelation, a page turned in a book whose sentences are written in light. The story also intersects with the practical. As telescopes and detection algorithms improve, we expect to find more such visitors. The first 2 interstellar objects surprised us because we had not routinely been searching for them. Now, with surveys that scan the sky nightly and instruments that filter moving sources, the discovery rate is likely to increase. Each new detection will add context and complexity, and the community will refine its models. It is a thrilling time. Astronomy is not merely cataloging the night, it is opening a new branch of comparative planetology that spans the galaxy. If you imagine yourself under a wide, quiet sky tonight, think of the scales involved. 3I divided by Atlas may be only a few kilometers across, but its history spans millions, perhaps billions of years. It crossed the gravitational scapes of unknown systems, survived the radiation between stars, and now, for a brief interval, reflects our light back to us. We are the better for watching. We are participants in a conversation not initiated by us, but welcomed by our instruments and curiosity. There are questions that will stay with us. Did this object originate from a protoplanetary disk similar to our own? Does it carry complex organics formed in a cold soda straw of space? Or did it keep only the simplest molecules? Could the materials on such bodies seed young planets with the ingredients for life? These larger queries connect the concrete spectral lines, particle physics, orbital mechanics, with the existential. How common might the conditions for life be in the galaxy? Each comet, each detection, nudges our estimates and widens our frame. And yet, perhaps the most profound takeaway is simple. The cosmos is vast, and in that vastness, chance does extraordinary work. A small body set loose by the dynamics of a distant planetary system finds its way into ours, and human minds, telescopes, and instruments join together to decode its story. The process is an expression of our species' peculiar strengths: curiosity, collaboration, and the patient transformation of numbers into narrative. So, as we close our eyes tonight, let us imagine the path of 3I divided by Atlas. A slow, silent voyage through starlight that carried with it ice and dust and the frozen memory of another Sunday. Think of the photons it shed as warmth reached its shadowed regions. Photons that took hours to travel, then days, then minutes across the void to meet our detectors. Think of the teams who triangulate its position, of the software that filters background noise, and of the quiet triumph when a spectral line reveals the unmistakable mark of OH. In the weeks and months to come, more data will arrive. Models will be refined. Perhaps future interstellar visitors will overturn current assumptions. Perhaps they will confirm that 3I divided by Atlas is a rare but instructive example of a water-rich interstellar body. For now, let us savor the encounter for what it is: a brief, luminous crossing of trajectories, a natural messenger from a distant system that stopped by, for a while, to share its secrets in ultraviolet whispers. Good night from Bedtime Universe. Keep looking up, not for salvation, not for spectacle, but for the quiet, stubborn knowledge that the universe is a place of variety, and that each new object we meet tells a small part of the great cosmic story. Sleep well, and dream of slow comets and distant suns. Welcome to Bedtime Universe. Tonight, we will drift together into a quiet sky and follow a visitor that arrived like a question. The sky opens like a slow breath. Stars hang like steady thoughts, indifferent yet intimate. In October of 2025, something old and deliberate slipped into that hush. Astronomers named it 3E Atlas, an ungainly label for an object that feels more like an argument between chance and meaning. It glows in the outer reaches of our system as if remembering some distant light, and every new image comes with a small electric shock of disbelief. At first, it was just data points, neat rows in a catalogue, a track across detectors, a velocity vector that did not match any known family. Then the first oddity appeared, a number so small it read like a dare. 3 Atlas shares a plane with Venus, Mars, and Jupiter with a probability calculated as 0.2%. Imagine throwing a dart blindfolded from another city and finding it lodged in the moving center of a target. The odds should keep us comfortable in ignorance, but they did the opposite. They made curiosity unavoidable. We learned a few things quickly. Its mass is enormous, 33 billion tons. It is not a wisp like most comets, but a thing with weight and presence. Hubble and other surveys revealed a teardrop-shaped glow. For a comet, tails follow the object, streaming away as solar wind and radiation push dust and gas into long wakes. This plume in front of 3 Atlas leads, as if the object is dragging a halo of light behind an invisible prow. Instruments aboard orbiters around Mars recorded asymmetric halos that shimmer with patterns resembling magnetic contours rather than random puffs. The James Webb Space Telescope returned a chemistry that did not fit familiar catalogues. The ratio of carbon dioxide to water ice was 8:1, a composition more at home in worlds we do not yet understand. And then there was the timing. Between the 21st of November and the 5th of December 2025, 3 Atlas would pass behind the Sun. For nearly 2 weeks, it would be lost in the Sun's luminous cloak, a strategic blind spot where no optical sensor or radar can follow. Astronomers named that stretch the cosmic curtain. The phrase feels theatrical until you stand beneath that invisible theater and imagine what happens when a performer disappears from view at the most convenient moment. If a natural wanderer, this disappearance is mere geometry. If engineered, it is an interval of opportunity. Hidden from us, 3 Atlas could change in ways we would not detect until it re-emerges. It could release smaller objects. It could reorient itself. The voice in the back of the room, the one that listens for symmetries and messages, began to whisper possibilities that felt both reckless and necessary. You should know the story of 2 earlier vagabonds. In 2017, a cigar-shaped visitor known as Oumuamua slid through the solar system, tumbling and accelerating in directions that made little sense under known physics. It arrived like a folded note dropped into the ocean. In 2019, a more ordinary interstellar comet named Borisov arrived and behaved like the textbooks promised. Between those two, the universe seemed mercifully ordinary again. 3 Atlas arrives as a third voice, one that borrows from both predecessors and then writes a new dialect entirely. Consider the physics we depend on to read these motions. Comets shed material as they warm, sodium and water vapor and dust trailing in predictable ways. Radiation pressure shapes tails, solar wind scours, sublimation sculpts. But 3 Atlas refuses to obey the script. Its tail does not trail. Its mass is heavy, but its light behaves as if guided by an architecture. The brightness patterns shift with a deliberateness that unsettles the models. For all of its familiarity with dust and rock, the object acts like an instrument. Some scientists say that great mysteries first arrive as stubborn data. Then, if they survive scrutiny, they become hypotheses. Avi Loeb is one of those who prefers hypotheses that do not shy from radical possibilities. The notion that this object could be a probe designed for patience sounds extravagant until you remember how many times the improbable became ordinary in science. Radio was once a novelty. Quantum tunneling once read like incantation. Black holes were metaphysical curiosities before they demanded pages of sober mathematics. Suppose for a moment that 3 Atlas is artifice. Suppose it is a construct assembled with patience longer than epochs. To cross interstellar space requires either enormous time or propulsion far beyond ours. A probe could be small and fast, or it could be slow and patient. Small and fast risks detection in every passing century. Slow and patient is cunning. A craft cast into the void, sheltered by cold and vacuum, drifting until the right lens finds it. If a civilization wanted to study another, it might not land. It might not send messages in radio frequency. It might send an object that operates in silence, that aligns itself with orbital planes, so that when a species reaches a certain observational capacity, there it would be